Hi, everyone. We are Egypt, Raquel, and Maria. We decided to further explore the Collatz conjecture. As you all know, the conjecture is pretty simple to understand, but we quickly realized proving it wouldn't be as simple. We broke up our presentation into three steps. First is our approaches, the approaches we took to tackling the conjecture. Second is quoting the conjecture. And three is analysis of patterns we found. First, we started by making a chart of numbers from 2 through 60 and we're trying to see if we found a pattern, and then we're also trying to find the stopping number. So as you can see, we started with 2 and then we went to 3. And then for 4 and 5, it's not on here because 4 and 5 are already on the 3 sequence and so on. So all the numbers are here from 2 all the way through 60. But that was only up to 60. So we were trying to figure out a way that where we could test larger or more effectively.
This is kind of where our code and analysis comes in. We wanted to keep analyzing the stopping number for as many inputs as possible. And so that led us to using Python to code the Collatz conjecture. And that is what you see right here. We further decided to analyze, again, how many steps it takes for input values to reach 1. So what we did here for this code was we limited it because the code would run forever to 100 numbers at first. And so how the code works is it starts at 2 because 1 is already at 1, and it counts all the way up to 100 and tells us and outputs in a graph the steps that number takes to get to 0. So as you can see, from 0 to 100, the largest amount of steps it took for any particular number to reach 1 was 120. And so as you can also note, there are certain values that plateau, meaning that some numbers actually took the same amount of steps to get to 1, which was incredibly interesting and not something that we thought we would find in the Collatz conjecture. So to further analyze these patterns and see if this is just unique to numbers from 1 to 100, we ran the code again, but for 500 numbers. And so that's what you see right over here. And running the code up to 500 numbers, we saw that these patterns continued. And now between 0 and 500, the largest amount of steps it took for any number to reach 1 was 140. And so that's how you can see that on this graph, it took 140 steps. And we note that some kinds of numbers took way longer to reach 1 than others. Some of them stayed between 0 and 60, whereas others would spike up to 140. But we still saw those plateaus as well here in this code. And so that's just something that we found really interesting. So again, we wanted to analyze even more numbers, and that's going to be this graph right over here. The code stays the same. The only thing we change is now it counts up to 1,000 numbers. And so again, when we were analyzing 1,000 numbers, now the largest amount of steps it took for any number between 0 and 1,000 to reach 1 was 175 numbers. And again, we can see that the pattern continues with numbers plateauing, meaning that some numbers will have the same amount of steps to reach 1. And that's something that we wanted to really analyze, kind of going into our next slides. And so just kind of understanding that these numbers plateau, we wanted to look a little bit more into them.
So I used Raquel's first graph of sequencing numbers up to 100, and I color-coded the groups of consecutive integers with the same amount of steps to reach 1. And so we noticed that a lot of these numbers had the same amount of steps. For example, 12 and 13 took 9 steps, 14 and 15 took 17 steps. 44, 45, and 46 took 16 steps. And so I basically color-coded by the line, and yeah, we can see a lot of patterns here. And I put these into a table form in Excel to get a better look at the patterns in these sequences. So I tried a bunch of trial and error. I looked at the space between these pairs to see if it meant anything. I looked for different properties of the numbers to see how it relates to the amount of steps. So for example, looking at the Excel I noticed that 12 and 13 and 84 and 85 both took 9 steps. And I noticed that 14 and 15 and 92 and 93 both took 17 steps. And so I was trying to look at a bunch of the properties to see if these had any relation to each other, why they took these amount of steps, why these two particular consecutive integers came up with that particular number. And so I ran into a wall basically, and it was kind of difficult to come up with a specific pattern for all these integers. And so this point, I tried something with the modulo. And so I took two consecutive integers, 8n plus 4 and 8n plus 5. And so I carried out the Collatz sequence for these, starting with 8n plus 4. And so we have 8n plus 4. We divide that by 2 since it's even. We get 4n plus 2. And we divide it by 2 again. We get 2n plus 1. And since that's odd, we multiply it by 3 and add 1. And we get 6n plus 4. And I'm going to stop it there because when we carry out the Collatz sequence for the next number, 8n plus 5, we are going to multiply it by 3 and add 1. We get 24n plus 16. Divide that by 2 since it's even. 12n plus 8. Divide it one more time since it's even. And we also get 6n plus 4. So at this point, these two consecutive integers have the same number in the sequence. And so from here, we can infer that the conjecture is true for consecutive numbers with 4 mod 8 and 5 mod 8 for natural numbers n. And it will take these consecutive integers the same amount of steps to reach one. And so looking back at our color coding chart, we notice that this is true for the pair 84 and 85. We take our first integer, 4 mod 8. So we subtract 4 from 84, we get 80, and that's divisible by 8. And then we look at 5 mod 8 for 85. We subtract the 5 from 85, we get 80, and that's divisible by 8. And so this is also true for the pair 60 and 61, and 76 and 77. And these all have the same amount of steps to reach one. And so looking at our conclusion now, using this, because of our code, we were able to determine that consecutive numbers that have the same amount of steps to reach one and are consecutively congruent to 4 mod 8 or 5 mod 8 will reach one. Though we cannot prove the entire Collatz conjecture, we can make an inference that these numbers will eventually reach one. Thank you.